Deep dive. Today we're tackling a really cutting edge area, video segmentation. It's becoming just so vital, isn't it?
Oh, absolutely. You see it everywhere, from video editing improvements to, robotics needing to understand the world visually.
Exactly. And that brings us to SAM2. Now, lots of people know about the original SAM, the segment anything model.
Right, the foundation. But SAM2, well, it records some really significant academic steps forward, pushing the boundaries.
Precisely. And that's our goal today. We want to really get into the weeds, go beyond just what SAM2 does.
We want to understand the why and the how. What are the core innovations, the, let's say, academic breakthroughs?
Yes, dissecting those novel aspects. And just for context, we're drawing mainly from our notes from April 26, 2025, and of course the key paper itself, SAM2, segment anything in images and videos.
A foundational paper for this area, definitely.
Okay, so where does the real innovation kick off with SAM2? What's the big first step?
Well, the most fundamental change, I'd say, is taking this idea of promptable segmentation and really extending it properly into video. They formalized this as the promptable visual segmentation task, or PVS.
PVS, okay, got it. So what's the essence of PVS? How does it work?
So basically, PVS lets you take a prompt, could be just a point, maybe a bounding box, or even a full mask on any frame in a video.
Any frame, not just the first one.
Exactly, any frame. You use that prompt to tell the model, this is the object I care about, and then SAM2 predicts what they call a masklet.
A masklet. Okay, like a small mask.
Sort of, but it's spatiotemporal. It represents the segmentation of that specific object across the whole video, or at least a chunk of it. It's thinking about time and space together.
Ah, I see. So it's not just segmenting frame by frame independently.
No, and that's a crucial difference from, simpler approaches that can struggle with consistency over time. This masklet concept really leverages those temporal links.
That flexibility prompting on any frame, that feels like a big deal compared to older methods.
It really is. A lot of earlier video object segmentation, or VOS, heavily relied on getting that perfect mask on frame one.
Right, which isn't always practical.
Not at all. SAM2 breaks free from that. You spot the object you want later in the clip. Fine, prompt it there.
And you mentioned refinement. The initial masklet isn't necessarily the final answer.
Correct. That's another academically interesting part. You can iteratively refine it, give it another prompt on a different frame, maybe where the first guess wasn't perfect, and the model updates the masklet.
Okay, so it supports a more interactive, kind of intuitive workflow.
Very much so. You guide the model more naturally.
But how does the model itself, the architecture, actually do this? Understanding across time must be the tricky part, right? Static images are one thing, but video.
You hit the nail on the head, and that leads us straight to the novel memory-augmented architecture. This is really where a lot of the academic innovation lies.
Memory augmented, okay.
Yeah, so to handle video effectively, you obviously need to use information from past frames. SAM2 does this with three main components working together. There's a memory bank, a memory encoder, and a memory attention mechanism.
Okay, let's break that down. A memory bank sounds essential for video. What's it storing?
Think of it like the model's short-term and medium-term memory. It holds memories of its past segmentation predictions, but crucially, it also stores the spatial feature maps from frames where you actually provided a prompt.
The feature maps. So like the visual patterns the model saw in that prompted area?
Exactly. Compressed representations of what it saw. These are kept in FIFO queues, first in, first out. So older memories gradually get replaced by newer ones, keeping it focused on recent context.
Makes sense. And you mentioned something else it stores?
Yes, object pointers. These are lighter weight vectors, more semantic. Think of them as little summaries capturing the GISC, or the core visual identity of the object being tracked.
Okay, so spatial features and these semantic pointers, how do they get created and put into the bank?
That's the job of the memory encoder. It looks at the model's current prediction for a frame and uses that to generate these memory features and object pointers. Then pop into the memory bank they go.
So the model is constantly updating its own history as it processes the video.
Precisely.
And then how does it use that history for the next frame?
That's where memory attention clicks in. It takes the features from the current frame, the ones coming out of the image encoder part of the model.
Right.
And it uses transformer blocks to basically compare and relate those current features to everything stored in the memory bank. It uses self-attention on the current frame's features, but also cross-attention to look back at those stored memories and the object pointers.
So it's like asking, based on what I see now, how relevant is this piece of information from the past?
Exactly. It weighs the past information, both recent visual details and the ongoing object identity, to make a better decision for the current frame segmentation.
That sounds incredibly powerful.
It is. And they didn't stop there. To really nail the temporal aspect, they embed temporal positional information into the recent frame memories. This helps model short-term motion explicitly.
Ah, clever. And what about when things get blocked? Occlusion is always a pain in video.
Yeah, they tackle that directly too. There's an occlusion prediction head, and they use learned occlusion embeddings. So the model tries to explicitly predict and handle moments when the object is hidden.
That's a very practical innovation, addresses a real-world headache.
Definitely. And one more thing on the architecture ambiguity. Sometimes, especially across frames, it might not be perfectly clear where the object boundary is.
Sure.
So SAM2 can actually output multiple possible masks for a given step if the user doesn't provide another prompt to clarify.
It has to choose.
Right. It uses a predicted IOU score intersection over union to pick the mask it thinks is most likely the best fit for that frame. Handling uncertainty like this is another neat academic point.
Okay, this whole memory architecture sounds like a massive leap from just processing frames individually.
It absolutely is.
Now, I remember seeing in our notes that a big part of this effort was also creating a new data set. SAV, was it?
Yes, SAV, the segment anything in video's dataset. You can't really train a model to segment anything in video without, well, a massive amount of video segmentation data.
Makes sense. And SAV delivers on that scale.
Oh yeah, it's huge. Currently the largest public video segmentation dataset out there. We're talking about 50.9 thousand videos.
Wow.
And within those videos, 642.6 thousand individual masklets. These spatiotemporal segmentations we talked about.
That's an enormous number. What about the content? Is it diverse?
They aim for diversity, wide range of geographic sources. They even included self-reported demographic info from the creators. Just good practice. But the really innovative part, academically speaking, is how they built this data set. They developed this multi-phase data engine.
A multi-phase data engine. Sounds complex. Walk me through that.
Okay, so phase one, they used the original SAM just for getting initial spatial mask on keyframes, like find objects in this still image.
Right, leveraging the existing tool.
Exactly. Then phase two, they brought in an early version of SAM2, one that could specifically take a mask as a prompt.
Okay.
They called it SAM2 mask. They used this model to take those initial spatial masks from phase one and automatically propagate them through time, creating draft masklets. This sped things up massively.
Oh, using the model itself to help generate its own training data, essentially. Clever bootstrapping.
Very clever. And then phase three, they used the full final SAM2 model, the one that can handle points, boxes, and masks as prompts.
The complete system.
Right. Annotators could now use any prompt type to refine things, leveraging the full memory capabilities of SAM2 for tricky bits. This made it even more efficient.
And I gather they mixed manual and automatic annotation.
They did. Some masklets were fully manually annotated or refined. Others were generated more automatically by prompting SAM2 on grids across frames to just get broad coverage.
Increasing density and variety.
Exactly. But crucially, and this is important for quality, every masklet, whether manual or auto-generated, went through a separate quality check by different annotators.
So a human verification loop, that's vital for dataset reliability.
Absolutely. So it's not just the sheer scale, it's the methodology and the quality control that make SAV significant.
And you said it dwarfs previous VOS datasets?
By a huge margin, about 53 times more masks than the next largest one before it. That kind of scale really unlocks the ability to train these more general promptable models.
Okay, so we have this novel architecture fueled by this massive new dataset. What does that translate to in terms of actual performance? How good is SAM2?
The results are pretty striking. First, let's look at just standard image segmentation. Even though it's designed for video, SAM2 actually beats the original SAM.
Oh, really? How so?
It gets higher accuracy with just a single click prompt, and importantly, it's about 6 times faster.
6 times faster. Where does that speed up come from?
Largely from using a different, more efficient image encoder called Hyura. It's pre-trained using MAE, mask autoencoders, which helps.
Okay, so better and faster on images. What about the main event video, specifically semi-supervised VOS?
Right, the task where you give it the first frame mask and let it run. Here, SAM2 significantly outperforms the previous state-of-the-art methods, and that's across multiple standard benchmarks, Davis, YouTube VOS, and importantly, also on their own SAV validation and test sets, which are designed to be challenging.
Outperforming the state-of-the-art is impressive. And you mentioned speed earlier.
Yes, it achieves real-time inference speeds, which is huge for practical applications, interactive tools, robotics.
Real-time performance on this kind of task is definitely a big step. What about the interactive PBS task itself, where the user provides prompts as needed?
They evaluated that too. They compared SAM2 against baselines, like combining the original SAM with existing VOS methods like XNEM++ or Qt. SAM2 wins again. It reaches higher accuracy with fewer user interactions needed, both in offline tests and more realistic online interactive setups. Basically, it gets the right answer with less effort from the user.
Fewer clicks for better results. That's the goal, right?
Pretty much. They also did some fairness evaluations using the demographic data and SAV. The results look generally positive, showing high performance across different protected groups.
Okay, good to see they're considering fairness. So performance looks strong across the board: accuracy, speed, interactivity, even initial fairness checks.
Yeah, the gains are substantial.
Let's circle back to the architecture for a moment. Did the ablation studies where they test removing different parts reveal anything particularly insightful about why it works so well?
Oh yes, ablation studies are gold mines for that. They confirmed, for example, that using that specific higher image encoder, pre-trained with MAE, was really key for efficiency and performance.
Okay, so the encoder choice mattered.
Definitely. Also, the way they structured the memory attention using those stacked transformer blocks with both self and cross attention, that specific setup proved crucial.
The interaction between current frame and memory is vital.
Exactly. They also found that their decoupled design image feature extraction from the video-specific memory parts worked well. The two components interact cleanly through the memory.
Interesting. Did they look at things like how much memory you need or resolution?
Yep, they systematically tested things like input resolution, how many pass frames to consider, the size of the memory bank, even the overall size or capacity of the model. They mapped out how these parameters affect performance.
So providing some guidance on trade-offs.
Right, and remember those object pointers in the memory bank, the semantic summaries.
Yeah.
The ablations showed that adding cross-attention specifically to those gave a noticeable performance bump, especially on the harder video datasets. They help maintain object identity over long, challenging sequences.
So those lightweight pointers punch above their weight.
Seems so. And one other interesting finding, they compared their direct memory storage approach to using something like a recurrent GRU network, which is a common way to handle sequences. Their simpler approach of just storing the memory features directly was actually more effective and computationally cheaper. Sometimes simpler is better.
Fascinating. These details really show the depth of the engineering and research involved. Now, no model is perfect. While SAM2 is clearly a big advance, were there limitations mentioned or things we could infer are still challenges?
Well, one thing is the phrasing around the PVS task definition, focusing on valid objects with clearly defined boundaries.
Okay, so maybe things that are fuzzy, amorphous, or not clearly object-like could still be tricky.
Potentially, yes. Things like water surfaces, smoke, or maybe very complex textures without clear edges might pose a challenge. It's geared towards segmenting things.
That makes sense. What else?
The fairness evaluation was a good first step, but as with any model, you'd need more testing in specific real-world applications to really understand potential biases in different contexts.
Sure, context always matters for fairness.
And they also noted that their calculation for annotation time saved is, a model. It's simplified and might not perfectly capture all the complexities of real annotation work.
A reasonable caveat. And thinking ahead, building on SAM2, what seem like the obvious next steps, where does research go from here?
Well, one clear direction is handling multiple objects simultaneously in a more integrated way. Right now, it's mostly focused on tracking one prompted object at a time. How do multiple objects interact? Can the model understand that context?
Multi-object reasoning and segmentation within the same framework.
Exactly. Also making that data engine even more automated, perhaps automating the quality verification step, could allow for even larger, more diverse data sets in the future.
Scaling up the data pipeline?
Right. And maybe integrating more high-level semantic understanding. Could the prompts be more complex than just points or boxes? Could you prompt with text, for instance, segment the person walking the dog?
Interesting possibilities. Integrating language understanding.
Definitely an exciting avenue.
This has been incredibly illuminating. It's clear SAM2 isn't just an incremental update, it's a really significant academic leap forward.
I agree. You've got this unified model for images and video. It's promptable, it has this novel memory architecture, and it's backed by this huge SAV dataset. It really pushes the field forward.
A powerful combination of architectural innovation and data scale.
Precisely.
So as we wrap up this deep dive, maybe a final thought for our listeners. Considering SAM2's ability to, segment anything in video with just minimal guidance, how could this fundamentally change how we interact with visual media?
That's a great question.
Think about content creation, video analysis, maybe even how humans and computers interact visually. If segmenting objects becomes this easy and intuitive, what does that unlock?
It really opens up possibilities, doesn't it? From much smarter editing tools to deeper analysis of video content for research or security to maybe even new forms of augmented reality interaction.
Potentially transformative stuff.
Indeed. And for anyone whose interest is piqued, the team released the SAV dataset, the SAM2 model, the code, even demos.
Oh, fantastic. So people can actually try it out.
Yes, they can dive in themselves and explore it firsthand. It's a great resource for the community.